Okay, thank you. Bob asked me to talk about an analysis technique that professional astronomers would like amateurs doing spectroscopy to consider doing to improve the usefulness of the results they produce. So, next slide, please. Amateurs record photometry and spectroscopy, but we rarely do that purposefully on the same object at the same time. And I'd like to show you this morning that doing this, you can potentially deliver results of real scientific benefit. And to do that, I think we first need to look at some of the issues around how we do spectroscopy. Next slide. We now have available to us a number of high-quality spectrographs. Amateurs are routinely using those to contribute data to various databases that have been set up. The guiding principle of processing amateur spectra is that we should be carrying out all of the processing operations on our raw 2D spectral images that require knowledge of the conditions, instrumental and atmospheric conditions under which the spectra were recorded. And if we do that, that should enable anyone using that spectrum to be able to use it without further knowledge of these observational conditions. So surely this is everything we can do to make these spectra useful, is it not? But if you look at the use of these databases by professional astronomers and their use in published literature, there really is not a great deal of use yet. So I would argue there is an exploitation deficit in this area that we should perhaps look at. Next slide, please. So let's talk about just the general processing of amateur spectra. As a general rule, spectra being submitted to these databases should be bias dark and flat corrected, wavelength calibrated, and corrected for instrumental and atmospheric losses using a reference star with a known spectrum. This usually will be a close-by star at the same air mass, probably ideally an A and B star because it will have a nice smooth continuum. And many times we use stars from the Miles spectral database, for example, which have got well-defined spectral profiles. In the absence of a Miles star, if you know the spectral type of the star of your target, you may be able to use a Pickles synthetic spectrum to use for as your reference star. But that's normally the level of processing required by any of these databases once you've done that. And the result is a spectrum as it would have been measured by a perfect instrument located outside the Earth's atmosphere, so a perfect Hubble Space Telescope. So we've done our job well. What's the problem? Well, I think the nature of these spectra may hold a clue. They're almost all relative flux spectra. Next slide. So what do I mean by a relative flux spectrum? It's a spectrum in which the relative level of the spectral flux is consistently represented across all wavelengths, but there's no definition of the absolute flux level in these spectra. So a relative flux spectrum is often normalized, in a sense fairly arbitrarily, to the value unity at some particular wavelength. And that sets an arbitrary scale on the flux dimension. The relative strength of spectral features is correctly represented within the spectrum, but it contains no information about their absolute strength. The spectrum is therefore qualitatively correct, but quantitatively is limited. Relative flux spectra may therefore be perhaps less attractive to a professional astronomer who are trying to carry out a quantitative analysis because they haven't the ability to get absolute fluxes and energies out of that spectrum directly. However, there is still much useful information in such spectra that can be extracted. Next. Particularly the equivalent width, which is very often used in papers that use these spectra. It's measured, and there's a formula that's traditionally used for calculating the equivalent width, and the little picture at the right-hand side shows you what we mean by that. If the red curve is they say an absorption feature in a spectrum, the hashed area is the equivalent width, which has the same area as that spectral feature. And it's a flux ratio, so On its own, it doesn't provide information about the absolute strength of any spectral feature. And if the area of the feature remains constant, but the continuum flux changes, then the calculated value of the equivalent width will also change. And that is a potential issue. It could potentially lead to misinterpretation if all you're looking at is the equivalent width. And I'll show you an example where that could occur later. Next slide, please. So a technique that's often adopted is to rectify a relative flux spectrum, by which I mean you effectively generate a smooth profile of the continuum, less any emission or absorption features, and you divide the spectrum by that smooth continuum. And that gives you a continuum which has the value unity everywhere, except where there are features in the spectrum. But it no longer contains information about variation of the continuum with wavelength. However, the relative scale of spectral features is preserved, and therefore it can be used to calculate and compute things like the ratio of spectral lines, which is what's often used to classify spectra. Next slide, please. So, picture that many of you will be familiar with if you have Graeme Corbely's book, that most of the spectra in there are have been rectified, so they can be displayed, and you can see the relative features and the variation of spectral features with spectral type. Where this doesn't work so well is if you're dealing with very red stars, which have got a continuum that's heavily punctuated with molecular absorption features. It's then very difficult to define what the smooth continuum is. So you'll find in Graeme Corbely, the red stars tend to be normalized spectra rather than rectified. Next slide, please. So could we do better? So what many professional astronomers would like is that we consider trying to provide spectrum calibrated in absolute flux units. By that I mean a spectrum of an object which provides quantitative measures of the spectral energy distribution in units such as ergs per square centimeter per second per angstrom, FLAM units as it's sometimes called. This contains more useful and potentially more usable scientific information. It enables measuring spectral energy being emitted in emission lines to be produced, or perhaps monitoring changes in continuum flux over time. Because you have the absolute information you need to do that. So how could we calibrate our spectra in absolute flux units? And at this point, we find that the professional and amateur worlds tend to approach this problem rather differently. Next slide, please. What the professionals do is to take advantage of the fact that their observatories are usually located at high altitude sites with photometric observing conditions. So they can therefore model the transmission properties of the atmosphere well and reliably, and therefore common practice is to measure spectrophotometric stars which have accurately known spectral energy distributions at different air masses during the night. And they can then use the modeling of that information to calculate the air mass dependent atmospheric losses and determine the SED of the target spectrum in absolute flux units. Next slide, please. We have a problem with adopting that technique. Usually we're working at low altitude under less than photometric skies, where the color is not the nice dark blue that you get on the tops of mountains. And so that method will generally not work. We have atmosphere with usually with variable amounts of moisture and dust content. Certainly moisture if you're in the UK, it may be dust if you're in the US, and I've got a forest fire going somewhere close by. One solution is to recognize that photometry using Johnson-Cousins standard photometric filters is in effect measuring the absolute flux of this part of the spectrum of the object being transmitted by the filter. You have to calibrate your filter to do that, but you do in fact have an absolute flux measurement with regular photometry. So a measurement of the V magnitude of an object obtained concurrently with the spectrum could be used to calibrate that spectrum in absolute flux, provided you cover the whole V filter passband, and that's an important point to bear in mind, but that for much of the lower resolution spectra that amateurs are collecting, that isn't a problem. We usually cover that whole V passband. If that was a problem, you could always go to different filters with narrower passbands. The method is applicable in different cases. And different filters, passbands could be used. You'll hear later in the conference talk about observing flare stars, which have most of the energy being emitted during flares is in the high energy, the UV part of the spectrum. So it's often, in that case, better to use a B filter rather than a V filter in a case like that. So adapting the method is sensible in depending on circumstances. Next slide, please. So how can you obtain concurrent photometry? Well, if you've got a second scope suitable for filtered photometry, you can use that. You may have that on a separate mount, or you may have it piggybacking on the telescope that's got the spectroscope. If you don't have a second scope, you can consider collaborating with another observer who may be located somewhere else, who is able to record the photometry. And that's often a very beneficial sort of collaboration to build up a team to do that. You need to make sure that all of the observations are accurately synchronized in time, obviously, but typically better than a second, which is not hard to do really with internet time signals, is easily achievable. But there's another way you can approach this. If you don't have the ability to record concurrent photometry, perhaps you're dealing with a star where there is photometry available, for example, in the AAVSO or the BAA databases. You can use that, for example, by taking averages, say a daily average of the V magnitude, and interpolating that to the time of your spectrum. Next slide, please. So before I describe in detail how to do this, which will take a few slides, let's look at a couple of situations where collecting spectra and absolute flux has been beneficial, just as examples. The first one is, which shows a potential problem of interpreting the results purely on the basis of equivalent width measurements alone, and where recording and calibrating an absolute flux will give you more complete picture of what is happening. And the second example I'll show you is where flux calibrating a spectrum can provide data that's both useful to professional astronomers, but actually more helpful to us amateurs to understand what might be happening in the object we're observing. So next slide, please. The first example is going to be based on observations of symbiotic stars, which are binary systems where you have a red giant transferring material to typically a white dwarf. There has been a project to observe those for many years that are being coordinated through the ARAS project in Europe. And there are many years now of observations of symbiotic stars in that database. Most of the observations that were made were not recorded with concurrent photometry at the time. So we're, in a sense, retrospectively having to try and see if we can calibrate these in absolute flux. I'm going to use as an example of one particular symbiotic Z Andromedae, which we have about 7 years of observations available to analyze. First, we have to find V magnitudes that we could use for this. So next slide. And one way of doing that is to use the AAVSO V magnitudes. And in the top graph there, you can see the blue points are daily averaged AAVSO V magnitudes. You want to be a little bit careful and check that there are not a lot of discrepant values of magnitude creeping into that. So you can do a little bit of filtering of the light curve before you do the daily averaging. But you can see there you've got reasonable coverage in time of the magnitudes that are available. And in the bottom slide, what I've done is I have linearly interpolated between the V magnitudes and the daily average V magnitudes to the times of the spectra we have in the database. And the little ticks along the top show you when spectra are available from the start. And an area of particular interest is where there was an outburst just at the beginning of 2018, which I'll explain in more detail on the next slide. Okay. what we want to do is to calibrate our spectra in absolute flux, as I said. Suppose we want to measure things in that spectrum. For example, symbiotic stars tend to have quite strong hydrogen Balmer emission lines. Let's say we want to look at the hydrogen beta line there during the outburst. You can obviously, even in the relative flux spectrum of that, you could calculate the equivalent widths. But because this has been calculated or flux calibrated in absolute flux, as you can see from the y-axis in that plot, we also have the ability to calculate the energy in that line by interpolating across the continuum on either side of the line underneath it and computing the shaded area in yellow above that interpolated continuum. So next slide, please. If we look at what's been happening during that outburst, the top plot there shows you the continuum flux now at h beta, which is how the continuum level in the region of the h beta line has varied in time. And it almost mimics the V magnitude, because what the V magnitude was measuring was essentially the rise and fall of the continuum. The middle plot there shows you the computed equivalent width of the h beta line, and the lower plot is the line flux we've computed by integrating the area of the filter. And next slide, please. If we just draw a vertical line through there, you can start to see the issue that might occur, because you can see on the middle graph the equivalent width takes a sharp drop at the point of that dotted line, whereas in the lower graph, the line flux in fact hasn't changed. There has not been a significant change in the flux of that line. Next slide. There was a paper that came out about that outburst, which made the comment that the equivalent widths of studied emission lines in general in optical spectra of ZN showed significant decline, as indeed they did. The plot at the top is the one that was in the paper, which very similar to the results we got from analyzing the ARAS spectra. But it doesn't tell you the whole story. In fact, what is more useful, I would suggest to a professional astronomer wanting to analyze that data and to have that data to, for example, use in modeling, is that the line flux in fact didn't change at the point of that outburst. Next slide, please. So why does all this matter? Just that calibrating an absolute flux can give you a more complete picture of what is actually going on, and that would be I would say, the strong motivation for doing it for us as amateurs, but also the professional astronomers get more useful data. Next slide, please. And the second example is WZ Sagittite dwarf nova, which went into outburst a couple of years ago now. It was a relatively rare outburst of this CV. It excited quite a lot of interest in the professional world. It was a bright outburst, as you can see, went up to almost 8th magnitude. We had a good AVSO V magnitude light curve. I took daily averages of that and interpolated them to the green points, which were the times of the spectra. As you can see along the top, the red dots in this case are the times of the spectra. Next slide, please. And what we're interested in is really in detail what was happening in those 4 regions. The first one is the initial bright outburst and rapid fade. But then, quite unusually, this went into a number of rebrightenings. And in fact, 3 of these were almost mini outbursts, complete outbursts in their own right. So we had a lot of useful data in our spectra about what was going on there. And as well as wanting to use that to be useful to us other astronomers, it would also be nice for us to see what was actually going on in these spectra during that time. Next slide, please. So what I've shown you here is the results of the analysis that we got by calibrating these spectra for each of the 4 outbursts that I circled on the last slide. The top plot, in each one I've just taken the spectra from one observer in each case, just to ensure as much consistency as possible. But in the top slide, you can see the spectral profile, spectral energy distribution from that star as it gradually faded from the first outbursts. And you can see significant changes in the spectral profile. Obviously, the slope has changed a lot, but the profile of some of the spectral lines, for example, H alpha is prominent, is purely in emission, whereas lines like H gamma have got quite a deep absorption trough in which the emission line is appearing. The lower slide is the second major outburst, and these are spectra from Pavel Dubovsky in Slovenia. And again, you can see gradually how it's changed, but by the end of that second outburst, for example, the emission lines in H gamma have virtually disappeared. It's just an absorption dip. Next slide. And for the final two outbursts, these are spectra that Woody Sims got, which again shows the progressive change in the energy in that star as it goes through the outburst. So I think these results demonstrate that what can be achieved by combining consistently calibrated spectroscopy with concurrently measured photometry. You get information about what's the physics of that outburst, which are potentially more useful than if these just were relative flux spectra. So next, please. So I just mention here as a taster for what you'll hear later on in the symposium. There'll be descriptions of a project on stellar flares, which several of us have been working on, where we've been using simultaneous photometry and spectroscopy to measure the energetics in the flares of these M-dwarf stars in a way which has been relatively rarely done in the professional literature before. And that's just a little montage of some of the thoughts that you'll find if you look in the proceedings and come along to the talks. You get them in glorious technicolor in the talks, which you don't get in the proceedings. Next slide, please. So how do we do all of this? I've talked a lot about calibrating and flux, but how would you, if you wanted to do it, how would you go about it? Well, the first thing is really to get the transmission profile of the V filter you're using. The one I have is the one from Astrodon, which seems to be the most common one, or at least it was before it became unobtainable. You can get that from the manufacturer, hopefully. You need to find what I've called the magnitude zero point, which enables you to relate your V magnitude to the absolute flux transmitted by that filter. And one way to do that is to use spectra calibrated and absolute flux. For example, the CalSpec archive from the Hubble Space Telescope. That is calibrated in flux units of ergs per square centimeter per second. And that's the link, but you just Google CalSpec and you'll be able to get them. Next slide, please. So what you do is you start you take the spectrum, just take one star from the archive. The flux calibrated spectrum is showing you at the top there. You multiply that by the transmission profile of your V filter, get the lower plot. Next slide, please. You then measure the integrated flux transmitted by the filter to get that value F. And in this example, it's the value shown there. And the CalSpec archive tells you that the magnitude of this star is 9.69. So the 0 point that you're trying to get for this particular star comes from that formula there. You're just changing that flux into a magnitude. And you can repeat this for several stars from the CalSpec archive and calculate a mean 0 point. Next slide. And there's the results I got. I measured a variety of stars, a variety of different spectral types and magnitudes, but they come out with a very consistent value for the 0 point, with a standard deviation which is encouragingly small. Next slide, please. So your 0 point is 13.629 magnitudes, and that then is the value for that filter for all subsequent work. You only need to do this exercise once. Now, supposing you're measuring a target, let's say VT is the V magnitude of your target measured at the same time as the spectrum, either measured or derived from, say, a database of V magnitudes. You can calculate the absolute flux of your target, which will be transmitted by the V filter using that formula there by plugging the 0 point in, along with the V magnitude of the target. You're now ready to convert your spectrum into absolute flux units. Next slide. So what you need is to go and take a relative flux spectrum of your target, corrected in the way I've described for atmospheric extinction and response, instrument response in the usual way. use an example, a spectrum of another symbiotic, AG Pegasi, as an example. You multiply that spectrum by the transmission profile of your V filter, you get the results at the bottom. Next slide, please. And you then measure the integrated flux in the transmitted profile of the relative flux spectrum. That gives you a value R, the total relative flux transmitted by the filter in units of relative flux. Now we know the V magnitude of AG Peg at the time that spectrum was taken is 8.62. So the absolute flux transmitted by the V filter is therefore, plugging the numbers into the formula, you get an absolute flux there. And that's your parameter A. So you've got R and A, two useful numbers. Next slide, please. What you do is you multiply your relative flux spectrum of the target by A and divide it by R. And that's easy to do if you're using something like ISIS, the arithmetic tab, for example. And as if by magic, you now have a spectrum calibrated in absolute flux units of ergs per square centimeter per second per angstrom. Now, if you want to ponder over that in more time and see, convince yourself this does work, there is a little report explaining basically what I've done there it's on the BAA website in the spectroscopy section with a horribly long URL, but so I've just given you a tiny URL version of it. And we can come back to that slide later if you want to write it down. But that just describes in words what I've shown you in pictures. Next slide, please. So finally, if you're skeptical like me and you're not sure, is this all true? Will this really work? What you should do once you've calibrated your own filter is go and test it yourself by measuring a star with your own spectroscope, say one for which you can get an absolute calibrated spectrum, say another star from CalSpec or from somewhere like the next generation spectral library, and go through the process. And what you should find, as I've shown you in that plot at the bottom, is that the two will virtually overlap. They will be essentially identical profiles. The method really does seem to work very, very well. Next slide, please. So just in summary, what I would suggest is that by calibrating your spectra in absolute flux, you're producing results which will certainly be more useful to professional astronomers and hopefully will in time result in more of amateur spectra appearing in professional publications. But it will also give you more insight into what you're actually measuring physically in the data that you're recording. And I think it more personal satisfaction and feeling of value in the data you're recording. Next slide. And the end. Thank you for listening, and I'm happy to take any questions. Stunned silence.
Yeah, I'm not going to talk about the process, but one of the issues that you brought up was the lack of use of amateur spectra by the professionals.
Yeah.
And I'm wondering if it's just that they don't know that ARAS and AV spec and things like that exist. Has there been a paper or poster given at like the AAS meeting that announces these things to the professional community so that they might be able to make use of it?
There certainly has been some work. I know that François Tessier is giving a talk at the European Astronomical Society meeting in Valencia later this month, which will essentially give examples of this sort of analysis that we're able to do. And he's been producing a newsletter that has been now indexed on ADS, again, that's showing some of the results that have come out of the use of amateur spectra, but it's a struggle. I think there's quite a lot of skepticism in professional circles that amateurs can be trusted to do a good job. And it is an uphill struggle, but I think if we do this sort of thing and write up papers and try and get things published in the mainstream literature, then gradually the message will get through that there's a lot of data there that amateurs are collecting and will continue to collect. But should be finding its way into other papers that other people are writing.
Probably a good idea for us to strive to get something into research notes of AAS, maybe get a presentation at one of the upcoming meetings, just to let the community know that there is a resource there. And I assume that's Valencia, Spain, not Valencia, California, right?
I'm afraid it's Spain, yes.
Gary.
The timing would be almost perfect because I think the AAS meeting coming up in January is in Tucson, which for Bob and Woody and a couple other folks is practically local. So
AAVSO will be in Tucson in November, and papers can still be submitted, I believe. In Tucson? Wow. Okay. Yeah. Yeah, we were hoping to have this AAS butted up against each other, but that didn't work out. Questions, comments? Anybody online? I'll tell you a personal comment. One of the things that for me was a real eye-opener several months ago, Woody and I were looking at some of his spectra. I think it was of one of these symbiotics. And if you plot it as most of us would, just as relative intensity, you saw that as the star was brightening, those emission lines kept getting smaller, smaller, smaller in relative intensity. Once you flux calibrate, you discover that what's happening is the emission line stayed exactly where it was. Continuum went up, 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 and swallowed it. So you get a whole different picture of what's going on the star when you treat it properly like this.
What you find, if you look into the professional literature, because it's relatively rare that spectra are absolutely flux calibrated, they rely a lot on equivalent widths, and you see it's equivalent widths that are published. And usually with a caveat to say that beware that the continuum may be changing during this, but it's not quantified, and therefore that's an area we, I think, can do a better job.
If you repeat that same calibration process with a different band, do you get the same absolute flux?
Yeah, you do.
You do.
You do, yeah. You've got to be careful because if you use the Johnson-Cousins filter, they're quite broad, and they can often virtually run off the end of where we have our spectra. So there's a bit of an issue there about making sure that you allow for there's a greater uncertainty comes into the calibration using that. E is really nice because not only is it in the middle of most of the amateur spectrographs, it tends not to have such strong emission lines in that part of the spectrum. So it's useful. But you can also, you don't have to use Johnson-Cousins filter. This will work with any filter profile. So if you want to do it with much narrower filter profiles, if you have the filter, use the same technique will work.
Yeah, Sloan might be good if you got a little higher resolution.
Yeah, you get
smaller
one with a
free
nice sharp cutoff, straight edges.
The other thing that we've seen on the flare star project is for a lot of us, it's a whole lot of equipment, claptrap to do simultaneous spectra on this telescope and photometry on this telescope. Partnering works greatly. A lot of the photometry that you'll see Saturday came from Gary. So that you say, hey, this is the star we're watching this week or this month. And you get photometry and Woody gets spectroscopy. You can do this to provide flux-calibrated spectra that way. Not important at all, because you're doing well-calibrated photometry. He's doing well done spectroscopy. The only thing is you want to overlap time. So we have a real problem with England and the US. You know, it's hard to get a time overlap, but you know, if you're, what you were in New Mexico. Okay, he's in Aubrey, you know, we're in Arizona, not a problem. It's dark most of the time for both.
What's interesting is we're also trying to coordinate our amateur spectroscopy and photometry with swift UV measurements of the same object at the same time. So what will come out of that remains to be seen. Tess is obviously also observing them at the same time, but we don't know. We haven't got the results yet.
Right. So it's, and I'll tell you, it's really fun to be collaborating with, like we were talking about astronauts, multiple people, multiple instruments on a single project, on a target, and it just absolutely magnifies the value of the data that photometry is.
It's also worth making a comment. This is probably one of the more positive benefits of the COVID pandemic, because it forced a lot of us to go online and start talking to each other via Zoom. And that created collaborations where people could on a weekly basis discuss what they were going to do, how they were going to do it, and get active in building consortia that in our case, was targeting a number of flare stars. So COVID's not all bad news.
I wouldn't get too distressed by professional acceptance of amateur spectroscopy. I think that there's a statistical factor working against the amateur community that's really tough to get around, and that is for, I'll stick my neck out here, just say for a very, very large percentage of the objects we're interested in looking at, a 2 to 4 meter telescope is a very small telescope. And that's just the hurdle against reality. So I wouldn't get too discouraged.
I think the other aspect to that is the sort of objects we can observe with our equipment isn't observed by the professionals very often because they're too bright.
Yeah, and we own the bright sky. Right, and we're the only ones watching. Anybody else? Eric, since I'm here with you, would you like to say a word about the spectra handouts? Oh, Eric?
I was just going to add that the other advantage the amateurs have is we get lots of time. So we can, I mean, you can't get a 5-hour block of time to do a time series on a 4-meter telescope, what the professionals tell me.
We need that 5 hours every night for a month.
No, I had just mentioned about Bhutan that while with me, a very small number of atlases and spectra of stars. There was some number of years ago. And I have a small number of them available here that you can have for the ridiculously low price of $20. If you find these on eBay, they are very expensive, they're quite rare. But if you'd like to take a look at one, they are nice spectra of 75 of the MK standard stars, ranging from G through M and NS, MC, SC, S, and C stars. So if you're interested, look me up someplace.
And bring your wallet. Thank you very much, David. Nothing from online. Those of you who feel a spark in your brain about getting involved in a collaboration like this with spectroscopy plus photometry, there is a sign-up sheet on the back table. We would love to hear from you. That concludes our morning session. I don't think I have anything else to report, so you can go off and have some lunch. And come back here at 1 o'clock for student presentations and CMOS workshop discussion. Yes, and I guess you could probably accept slides for tomorrow morning's presentations also. Okay, so do. Do you have the student presentations? Okay, thank you very much. We'll see you all at 1 o'clock.